in the computer science department on campus, so you can find him just, the short shuttle right away. And his PhD was from Stanford, and his work is about this super interesting, versatile, useful for everybody here type of stuff. So I'll let you take it from here.
All right. Thank you. Right. So welcome everyone. All of us know that constraint satisfaction problems are essentially very useful to AI problems, right? So things like the 8 queens problem or the Sudoku or planning problems coming from more real-life domains or even model-based diagnosis problems, all these can be modeled as constraint satisfaction problems or some optimization variants of them. So in fact, CSPs are so useful to AI that they're often referred to as AI complete problems, which means that if you can solve CSPs or optimization versions of them efficiently, then that certainly has a broad range of implications for AI problems in general, right? So what I'm going to show you in this talk is basically 2 algorithmic techniques that have this remarkable property that they're going to allow us to look at the constraints. They're going to allow us to solve combinatorial problems by essentially looking at the constraints only one at a time, right, very locally. And yet they would give us the right to make global inferences. And because we can localize our reasoning so well, we suddenly have this kind of an uncanny intuition into the nature of our combinatorial problem, essentially just by eyeballing it, right? And so what I'm going to do for this talk is not only talk about the methodologies of these techniques, but the various applications of them, right? Okay, so let's quickly look at what a constraint satisfaction problem is. A CSP is characterized by a bunch of variables, n variables x1 through xn, and each variable xi has a discrete domain di associated with it, from which it can take values. And on top of these variables are a bunch of constraints, m constraints c1 through cm, and each constraint specifies for some subset of the variables what the allowed and disallowed combinations of values to them are, right? And the goal is to come up with an assignment of values to all the variables from the respective domains such that all the constraints are satisfied, okay? Let's look at an example. So let's say the 3 coloring problem. How can that be modeled as a CSP? Well, we are given a graph like this, an undirected graph, and we need to color the nodes of the graph using one of 3 colors, red, green, or blue, right? Such that no 2 adjacent nodes get the same color. The way we model this as a CSP is essentially every time I have a node, I create a corresponding variable. Its domain is just the set of colors that I can use, red, green, and blue, right? And every time 2 nodes are adjacent, I create a constraint between them. Right, for example, x3 and x4 are adjacent here in the graph, so I have a little constraint between them, where the ones indicate allowed combinations and the zeros indicate disallowed combinations. So x3 equal to red and x4 equal to red is a disallowed combination indicated by a 0, but x4 equal to green and x3 equal to red is an allowed combination indicated by 1 and so forth. Right? So very trivial stuff. So the only thing I want you to notice here is that the matrix representation of a constraint really depends on the ordering of the domain values I have chosen here, right? I could have just as well written down this constraint by permuting any of the rows or columns in there, right? There is nothing in a CSP itself which gives you an ordering on the domain values of the variables, right? So now the question is, if I assume an ordering on the domain values of all the variables, or if I'm given one, and often I'll show you that it's very natural to the problem that we're solving. If I have a domain ordering on the values of on the domain values of all the variables, then is it going to be any easier for us to identify tractable class of constraints, right? And the answer to that is in the affirmative. And one of the cornerstone results is the idea of smoothness, which I first published about in 2005. Here is the definition of smoothness, right? So remember that we have an ordering on the domain values of all the variables, right? That's what we are working with. So here is xi, its domain values, xj, its domain values, laid out like this. Let's say that we have only binary constraints in the system for now, right? So a constraint is said to be smooth if the following property is true in its matrix representation, right? So at every 0, that means at every infeasible point, right? There exists 2 directions, like the ones that you see here, okay? Such that moving along at least one of these two directions decreases the L1 distance, that is the Manhattan distance, to a feasible, okay, this thing stopped working, to a feasible point, no matter where it's placed in the feasible region. Okay? So let's think about that statement for a second. What I'm saying is, you have to come up with a pair of directions at every 0, right? Such that no matter which one you have in mind, maybe this one here, but it could have been this one here as well, right? No matter which one you keep in mind, at least one of the two directions takes me closer to you. So let's look at an example. Let's say that you have that one in mind, okay? But it could have been that one, that's fine, but I'm just giving you an example, right? So let's say that you have this one in mind. So this direction at this 0 brings me closer to you in terms of the Manhattan distance, the L1 distance, although the other direction takes me away from you, all right? So for this 0, both directions bring me closer to you in terms of the L1 distance. How about for this 0? Yeah.
Manhattan distance between which two?
Between the point that you're considering, the whichever one you keep in mind, and the 0 that we're talking about, right? So at this 0, for example, if you move, so I'm comparing this position and that position, right? So if I move in this direction, I get closer to this 1, although the other direction takes me away from you. Right? But that's fine. At least one of the two directions should bring me closer to you. Right? And if you notice, this qualifies as a smooth constraint because the same two directions would have worked at every 0 even if you had kept any other one in mind. So let's look at this one. Right? Even if you had kept this one in mind, the same two directions would have worked at every 0. Right? Because this time, this direction is bringing me closer to you here, for example, at this 0, although the other one takes me away from you. Right? So is this definition clear? So at every infeasible point, there exists two directions such that moving along at least one of those two directions decreases the L1 distance to a feasible point no matter where it's placed in the feasible region. Yeah, question?
So by direction, you mean just,
Exactly, right. So what does it mean to move in a certain direction? It means change the current value of xi from di3 to di2, for example, moving in this direction. Right? Okay. What does it mean to move in this direction? It means, essentially go from this square to this square, which means changing the current value of xj from dj1 to dj2. Okay. So these are examples of a smooth constraint, but here is a constraint that is not smooth, right? Because the required pair of directions exists at every 0 except this one little guy here, where the required pair of directions do not exist. In some sense, that's because the ones lie on 3 sides of it. Okay? Question?
No, so can you give us intuition why, 2 directions?
I will tell you about it, yes. It's all coming up. By the way, I also want to tell you that this is not some contrived class of constraints that I'm going to talk about, right? In fact, many other tractable class of constraints that various other researchers had identified as being tractable, bearing different intuitions in mind, they're all smooth constraints. Okay? So this is kind of a unifying theme. Yeah.
What is smooth about?
Well, I mean, the fact that it's kind of 2 directions instead of like, you could conceive of, where you could have 3 directions at every infeasible point such that, moving along at least one of these 3 would decrease some kind of a distance metric. But since it's 2, since it's limited, it's kind of like smoothness. So. All right.
3 would be more smooth then, or?
No, 3 would be less smooth, right? Because, I mean, if you have a single direction, what does that mean? It means that essentially it's convexity, right? If you have a single direction and decrease the L2 distance to a feasible point, no matter where it's in the feasible region, that's basically convexity. But smoothness is, you're speaking about the L1 distance, not L2 distance, and you have a pair of directions instead of one direction. And I'm going to give you examples of how all these wonderful known tractable classes of CSPs are basically all smooth, right? It's coming. But right now what I want to tell you is that smooth constraints are amenable to a very simple randomized algorithm, right, for solving them in polynomial time. And here is the way it works. We start off with an initial assignment to all the variables from the respective domains, right, an arbitrary initial assignment. And every time I have a violated constraint, right, I just look at the projection of the current assignment onto this constraint. It must be a 0 because that's the reason why it's violated, right? And by definition of smoothness, there exists two directions at the 0. I randomly move in one of them and I'm done. That's the entirety of the algorithm. Okay, and like I said, what does it mean to move in a certain direction? It means, what does it mean to move in this direction? Changing the current value of xj from dj1 to dj2. What does it mean to move in this direction? Changing the current value of xi from di1 to di2 and so forth. Okay, so this is the entirety of the randomized algorithm, which we start off with an initial assignment. Doesn't matter which one. Every time I have a violated constraint, I just look at the projection of the current assignment onto this constraint. There are two directions defined at the 0. And then I randomly move in one of them, and that's it. Okay. First of all, before I tell you why this algorithm works, I'm going to give you an example so that some of the confusions might be. We can address that right away. So here are 3 smooth constraints. Okay, one between x1 and x2, one between x2 and x3, and one between x1 and x3. All right. So there is a satisfying assignment here. The pair of directions at every 0 are indicated, right? There is a satisfying assignment here, which I call A star, right? And that assignment is x1 equal to 2, x2 equal to 2, and x3 equal to 2, right? And the projection of that assignment onto each of these constraints is indicated by this red circle here. Okay? There is a satisfying assignment. But let's say that initially we started off with an assignment by where I assigned x1 equal to 1, x2 equal to 1, and x3 equal to 1. The green squares that you see here, right? That's the projections onto the individual constraints, all right? So now what is my algorithm saying? It's saying, look at some violated constraint, doesn't matter which one. Let's say this violated constraint. Okay, there are currently 2 violated constraints, and what is the L1 distance between the satisfying assignment and between the true assignment and the current assignment? It's 3, right? Because it's 2 minus 1 plus 2 minus 1 plus 2 minus 1. The current L1 distance between our assignment that we're working with and the true assignment is 3, and the number of violated constraints is 2, right? So I'm going to look at some violated constraint, doesn't matter which one, let's say this one here, and there are 2 directions at the 0, right? I randomly move in one of them. Let's say we made a random choice to change the current value of x2 from d21 to d22, right? So what does our current assignment become now?
Sorry.
Yeah.
Sorry, I'm not sure how you compute the L1 distance here.
L1 distance is just the Manhattan distance.
Just
But
you do it for every constraint or
right, so you could think of an L1 distance in this constraint here. Plus, there is also a well-defined notion of L1 distance between 2 complete assignments, right? So what is the L1? So there is a ranking. So what does this mean? So every domain has an ordering, right?
Yeah, so the L1 distance between the green box and the red circle would be 2, no?
In this constraint.
Yeah.
But I'm talking about a complete assignment to all the variables.
Okay, so just kind of going over the
I mean, both these notions are well defined. That's what I'm saying, right? There's a notion of an L1 distance between 2 complete assignments,
okay.
right? Plus, you could think of it as being within a constraint, right?
But yes,
Yeah.
the L1 distance is 3 is between 2 assignments because you
Between correct, right? Yeah.
And you know that L1 distance between the correct assignment and the current assignment without having the correct assignment.
No. I'm not claiming that. All I'm saying is that there is some satisfying assignment A star. I'm giving you an example, right? So we started off when I initially chose my assignment, right? The L1 distance to the true assignment, which I don't know what it is, right? But in this example, it's 3 right now, okay? And the number of violated constraints is 2, as we started the problem, right? So when I change the current value of x2 from d21 to d22, what happened here, right? What happened here is that now our satisfying assignment is still the same, x1 equal to 2, x2 equal to 2, x3 equal to 2. What happened to our current assignment? Our current assignment, only one variable changed, right? x1 equal to 1 continues to remain the same, but x2 is 2 now, okay? And x3 continues to remain 1. So what happened to the L1 distance? It decreased, right? It became 2 now between these 2 assignments. But what happened to the number of violated constraints? It increased to 3, okay? So the number of violated constraints increased, although the L1 distance decreased, okay? So this is important to remember because my argument is going to be on the L1 distance. It's not going to be on the number of violated constraints to prove why this randomized algorithm works. I'm going to make an argument on the L1 distance. So don't get confused with the number of violated constraints. Okay? So every time so in every iteration of the algorithm, what is going on? The projection of the current assignment onto this constraint is a 0. Like I said, that's the reason why it's violated. The projection of the true assignment, which satisfies every constraint and in particular even this one, right? That projection must be a 1. Okay? But I know that at least one of the two directions associated with the 0 will bring me closer to the 1 no matter where it's placed in the feasible region. So if I do it at random, there's a probability of at least 0.5 of decreasing the L1 distance between the current assignment and the true assignment.
Can you clarify what do you mean by projection?
Projection means that, okay, let's say that here, our complete assignment is x1 equal to 2, x2 equal to 2, and x3 equal to 2. Does this constraint involve x3 at all? No, right? So this constraint is just between x1 and x2, right? So the projection of our assignment, this complete assignment, onto this constraint is only the relevance of x1 and x2 here, right? Right? So that's really the algorithm, that's really the reason why our algorithm works. Every time I have a violated constraint, right, the projection of the true assignment is a 1. The projection of the current assignment is a 0. But every violated constraint gives me a chance to get closer to the true assignment with a probability of at least 0.5. Okay? So, and let's quickly review some of the standard results in random walks. So let's say that we have a random walk scenario on a graph, right, where we start off with some node in an undirected graph, and we randomly jump to one of our neighbors in every iteration. And if we're doing this random walk on a linear undirected graph like this one here, then it's well known that the expected number of iterations to reach the left end point starting from the right end point is only quadratic in the total number of internal nodes. All right. So what I have here in our algorithm is a directed version of that scenario, where the probability of going to the left could potentially be greater than the probability of going to the right. Okay? So which means there's a general attraction towards the left. Alright, so the expected number of iterations to reach the left end point starting from the right end point can only be less than in the previous case, and it too is quadratic in the total number of internal nodes. What do the internal nodes of a random walk represent here? They represent the different values of the L1 distance between the current assignment and the true assignment. Okay? And because the maximum L1 distance between any two complete assignments is n times d, where capital N is the total number of variables and capital D is the size of the largest domain, we are done in n squared d squared iterations. It's a very deceptive argument, right? Because we are doing it on the L1 distance, not on the number of violated constraints. Okay? Question?
Does this mean that the number of your constraints might increase and suddenly they will all get satisfied?
Correct. Yeah, that could happen. Yeah.
So could you imagine doing something like Boolean where you're officially high probability, you're free to make mistakes, and then as your temperature increases,
Right.
you actually don't want to be very conservative about it.
Right, but those are more like heuristic approaches, right, for simulated annealing and stuff. But what I'm saying here is there's a well-defined property of constraints called smoothness, where it doesn't even matter whether you're reasoning about the number of violated constraints. It's a very local approach. You look at some violated constraint, and every violated constraint gives you a chance to get closer to the true assignment.
In practice, which is
In practice, this is, for smooth constraints, this is humongously faster than actually in the AAA paper that we wrote this previous summer. It's especially well suited for distributed settings because it's such a local approach. Right? Yeah, question.
I just try to understand why you need to do the random walk, because you want to minimize the L1 distance.
Right, because we don't know what the true assignment is. So we don't know where it's going to fall within the feasible region of any constraint, right? So let's say that I always chose one direction, right? Let's say that I always chose to do it in this, maybe in this direction, right? When I'm here, let's say I always chose that one. Well, what happens if the projection was here? Then I'm moving away, right? But at least if I did it at random, there's a probability of at least 0.5 of decreasing the L1 distance, right? Yeah.
And you're not determinizing it because you could come up with an adversarial system of constraints that would.
Exactly, it's the power of randomization essentially, right? Yeah, Thomas?
What kind of problems exhibit this smoothness?
Lots of them. I'm going to show you examples, right? All right. So it turns out that various other kinds of constraints that people had discovered as being tractable, bearing different intuitions in mind, they're all basically smooth constraints, right? 2-sat, for example, if you look at a 2 cross 2, 0, 1 matrix, no matter how you arrange the zeros and ones, it's basically going to be smooth. Implicational constraints, binary integer linear constraints, simple temporal constraints, the so-called connected row convex constraints, which are the Gaussians in the world of constraints, right? So they too, the feasible region essentially looks like this for a connected row convex constraint, right? And they too exhibit this property of smoothness. And there are various others. I mean, it's especially useful in the context of temporal reasoning, like I will show you. Okay. All right. So before I show you the applications of this idea in temporal reasoning, I want to make a few quick comments about where the other applications of smoothness. So it turns out that not only the time and space complexity of this algorithm are so much better than its deterministic counterpart. By the way, there is a deterministic algorithm for solving smooth constraints, which essentially first establishes path consistency, which means that it makes some implicit constraints explicit for every triplet of variables, and then it does a backtrack-free search, right? But it's an expensive operation, okay? The deterministic algorithm is expensive. Yeah, question.
So how is this different from Walksat's algorithm?
No, because there is no, a walksat is an incomplete procedure, right? There is no guarantee that you would find a solution if there existed one. But this is a randomized algorithm. My probability is on my internal coin flips of the algorithm. It's not because of the adversary who's going to design the input. I don't care. I mean, my algorithm will work for every input. The probability.
I mean, just algorithmically, is it Walksat also it goes into
No,
violated
walksat reasons about the number of violated constraints and whatnot in your neighborhood, right? When you try flipping a variable in your neighborhood, then it reasons about, okay, how good is it to flip this variable in terms of, how many constraints I'll be newly violating, or how many constraints that were previously violated will now be satisfied, and all these kinds of metrics. But this is not that. We don't even look at the other constraints. We look at only one constraint at a time. Right?
empirically, do you find that your method performs
Much better.
Walksat actually?
Right. For smooth constraints, yeah, much better. Orders of magnitude better. All right. So not only was the randomized algorithm, space complexity and time complexity was so much better than the deterministic counterpart, but also because it's such a local approach, it's particularly well suited for distributed settings. All right. Which means, notice that we did, while solving smooth constraints, we did not do constraint propagation. We did not make implicit constraints explicit. All we did was work directly on the constraints, and every time we saw a violated constraint, we flipped a coin. That's all we did. Okay? And because of that, it's particularly well suited for distributed settings. And, as a matter of fact, we don't even exchange information about inferred constraints and compromise privacy issues. Right? And by the way, I mean, you can look up the empirical results of this paper that we presented in AAAI last summer. For smooth constraints, because this algorithm is so local and so efficient, we simply blow everyone else out of the water for smooth constraints in distributed settings. All right, one other quick comment before we move to temporal reasoning. So this is about the application of smooth constraints in the context of logical filtering. All right. So the problem of filtering is where you're given an initial state, perhaps with some uncertainty, right? And you have a transition to the next state, perhaps with some uncertainty again. And there are some noisy observations that you can make. And then there's one more transition, one more set of observations, and so forth, right? And now the idea is you want to maintain a compact representation of your current belief state that does not scale with this time t here, that is indefinite with respect to this. Right? And if I were to give this problem to you, the first thing that would come to mind is essentially the Kalman filter. If you have linear transition models and Gaussian noise, that would be the Kalman filter. But one could ask the question, what is the logical equivalent of the Kalman filter in the world of constraints? Suppose our world was described using only constraints, right? Instead of linear transitions and Gaussians, right? Only constraints. Now the question is, what is the logical equivalent of the Kalman filter, right? Once again, the answer to that is smooth constraints. The path consistency algorithm for solving smooth constraints is the exact logical equivalent of the Kalman filter. So much so that even the complexities match, the quadratic space complexity, right? Plus the cubic time complexity for updating your belief state. One more quick comment before we move to temporal reasoning. The idea of tree convexity. Right? It turns out like the way I defined smoothness, I defined it in terms of the L1 distance between the current assignment and the true assignment, right? But it doesn't have to be the L1 distance. Just by changing the distance metric, I can identify newer and newer tractable class of constraints. So this notion of tree convexity, which is a generalization of the idea of convexity, is essentially amenable to the same random walk strategy. Okay? So we are going to have instead of embedding the domain values of all the variables in a linear ordering, we're going to embed them in a tree structure. All right? And by the way, these kinds of problems actually arise in scene labeling problems in computer vision. So the domain values of every variable, there is no linear ordering, but they're embedded in a tree structure. So here is the tree for xi, here is the tree for xj, right? And if the image of any subtree in one variable's domain also happens to be a subtree in the other variable's domain, then these kinds of constraints can be solved essentially using the same random walk strategy that we had before, except now that I'm going to do a random walk up and down the tree instead of to the left and to the right. And I can still prove the convergence of it in quadratic time. Yeah.
If there is no true assignment, and basically, but there is an assignment that violates the least number of constraints.
No, this wouldn't find it. Yeah. If there, so it's a randomized algorithm, which means that essentially, if there is no solution, then so if there is a solution, you would discover it within a certain number of iterations, and you can quantify it, your error probability, right? And you can drive down this error probability using amplification lemma, essentially, doing it multiple times over. So if you don't find, if it doesn't come back with a solution, then you would have a very high degree of confidence that there is no solution at all, right? But this is not the same thing as the incomplete procedures, right? Because in the incomplete procedures, I'm just hoping that my adversary doesn't come up with a worst case input for me. But here I'm not hoping that. My probabilities are all over the internal coin flips of the algorithm, not about the adversary.
Just to recap, so there might be a case that there is a solution and you don't find it?
No, that's not the way to think about it. So there is so the only way that can happen is my coin flips turn out in a way that it wouldn't allow me to find it, right? But that happens with such a low probability that a hardware fault is even more likely.
The reason I'm asking is whether the perturbability is inherent in the smoothness, or it's an approximate perturbability.
No. So well, there is work in the pseudo randomness community which says that if you have a polynomial time algorithm for solving a problem using randomization, it's very likely you would be able to solve it even without using randomization. So when we have a randomized algorithm like this for solving a problem, it gives us confidence that we are very likely to find even a deterministic algorithm for solving it, right? So yeah, this is not incomplete solvers. This is randomization, which means that everything is on the internal conflicts of the algorithm. So let's look at some of the applications of smoothness in the context of temporal reasoning. In temporal reasoning, you are given a bunch of events which essentially can be modeled as these variables x1 through xn, and their domains are just the entire real number line, just because we are representing continuous time. And to establish a frame of reference, we have the special variable x0, which represents the beginning of the world, so to speak, right? And by convention, it is set to 0. And there are constraints on these events which essentially speak about the relative execution times of two events, right? So xj minus xi between some bounds L and u mean that the execution time of xj should be between L and U seconds after the execution time of Xi. All right? So that's called as a simple temporal constraint. Okay? And we could also have disjunctions of such constraints where we say that, okay, so there is some constraint of the form S1 or S2 and so forth, where each of these disjuncts is a simple temporal constraint by itself. Right? And one reason why disjunctions might arise is because of resource contentions, for example. If there are two processes that require the same resource, well, you have to make sure that one of them finishes its execution before the other one starts, or vice versa. So that introduces a disjunction. Right?
Can you give us some example on an application in that we need a simple temporal constraint?
Sure, yeah. I mean, simple temporal constraints is just so commonplace in AI, but I mean, I could give you an example. So let's look at this, right? I mean, so here is our X0, maybe it's the beginning of your day or something, at 12 a.m. or something, right? So here is the amount of X1 is the time you wake up, right? Under this X2 is the time you get going to your work or something like that, right? So, and there are all these constraints which say that you have to be back home by 3 p.m. and then, it's like constraints between the events that happen in your day, right? And you need to kind of find a consistent schedule for all of them, right? Which means an assignment of execution time to all these events such that all these constraints are satisfied. The way to graphically represent a set of simple temporal constraints is to have this directed graph, right? So an edge from X2 to X3, for example, annotated with this bounds 3, 5, are essentially encoding the constraint that X3 minus X2 is between 3 and 5. So it's just a graphical representation for your set of simple temporal constraints, right? And because these are just difference inequalities, which is a special case of linear inequalities, they are solvable in polynomial time, right? But there is a cleverer way of solving simple temporal constraints, which exploit the specific structure in this constraint here, where you kind of, for every edge that you had here, you compile it into two edges in the distance graph representation. So under the semantics that whenever xj minus xi is less than w, I have an edge from xi to xj annotated with w. Right? So for example here, x3 minus x2 was less than 5, therefore I have, that's right, x3 minus x2 is less than 5, so therefore I have an edge from x2 to x3 annotated with 5. So this constraint also says that x3 minus x2 is greater than 3, in other words x2 minus x3 is less than minus 3, right? So therefore I have a reverse edge from x3 to x2 annotated with minus 3. Right? Now what is interesting about the distance graph representation is that these set of simple temporal constraints that you gave me are going to be consistent if and only if there is no negative cost cycle in here. So the absence of negative cost cycles characterizes the consistency of my simple temporal constraints. Okay? And if there are no negative cost cycles, one such consistent schedule is given by assigning to every time point the length of the shortest path from x0 to that variable. Okay? So which means that there's a strongly polynomial time, shortest path computation based algorithm for solving simple temporal constraints. Okay? But I'm going to show you a very weird algorithm for solving simple temporal constraints based on the notion of smoothness. But there is a benefit of it. Okay? I'm going to tell you what that benefit is, but right now I want you to develop the intuition. Right? If you look at any simple temporal constraint, once again, this is a strategy that allows us to look at the constraints only one at a time, right? So if you look at any simple temporal constraint, say xj minus xi is less than or equal to c. What is it saying in its geometry? In its geometry, it identifies some feasible half space, some infeasible half space, right? Here I claim the required pair of directions at every infeasible point, okay, to establish the notion of smoothness is like this, right? So at every infeasible point, there exist two directions towards the axes themselves, such that moving along at least one of those two directions brings me closer to a feasible point, no matter where it's placed in the feasible region here. Okay? So one strategy for solving simple temporal constraints, not a very good strategy, but one potential strategy is to start off with an initial assignment to all the variables, right? And every time I have a violated constraint, I increase or decrease the value of one of the participating variables by an amount delta. And I do this random walk. Okay? The only problem with this approach is that we're dealing with continuous domains. We could have our current assignment A and the true assignment A star arbitrarily close to each other. Still on opposite sides of the line, of course, but they could be arbitrarily close to each other. Which means that if I increase or decrease by an amount delta, I could potentially overshoot A star. The only way to take care of that is to make delta really, really small. But if I make delta really, really small, it can only increase the number of iterations for convergence. Right? So, but there is a benefit of looking at it this way, at least gaining intuitions from this diagram. The thing is that this simple temporal constraints are not the only constraints that exhibit this property of smoothness. There are other constraints which do that as well, and in particular even those which have disjunctions. Right? So let's say I have a disjunctive a disjunction in my temporal constraints, saying that some variable xi should be between L1 and U1, or between L2 and U2, or between L3 and U3, and so forth. Right? So if you look at the geometry of this is smooth as well. Why? Because at every infeasible point, the required pair of directions are to the left and to the right. Okay? And even this disjunction, where some variable xi is constrained between L1 and U1, and some other variable xj is constrained between L2 and U2, well, the feasible region occurs in the form of a plus sign, and the infeasible region in the form of 4 quadrants. Once again, the required pair of directions at every infeasible point is towards the arms of the plus sign itself. Okay? So now I can go back, so let's call this a type 2 disjunction, and this one a type 3 disjunction. Right? So now I can go back and compare the shortest path computation algorithm for solving simple temporal constraints and the random walk strategy. The shortest path was clearly strongly polynomial time. We had no reason to be doing the random walk strategy at all. Okay? The good thing about the random walk strategy is that it is not tailored to simple temporal constraints. There are other kinds of constraints it can handle as well, namely those disjunctions that I showed you. Okay? So now I want to get the best of both the worlds. I want a strongly polynomial time, deterministic or randomized algorithm for solving these disjunctions in temporal reasoning. Okay? And by the way, this piece of work that I presented in the ICAPS conference in 2005 actually won the best student paper award at that time. So. Okay, the first idea is to view this as a meta-level constraint satisfaction problem. So I'm going to associate a meta-level variable with each disjunctive constraint, right? And the goal is to pick a disjunct from each of these disjunctive constraints such that the induced set of simple temporal constraints would be consistent. Right? And we know that for simple temporal constraints, consistency is characterized by the absence of negative cost cycles. Okay. Let's say that so every time I pick a disjunct here, so I have to pick, I'm going to associate a meta-level variable with each of these disjunctive constraints. The domain of such a meta-level variable would just be the individual disjuncts. So I have to pick one disjunct from each disjunctive constraint such that the induced set of constraints are going to be consistent. Every time I make a commitment to one of these disjuncts, that's really a simple temporal constraint right there, right? So every time I make a commitment to one of these disjuncts, what is it saying? It's saying I'm committing to xi being between L1 and U1. If I pick this disjunct for this constraint here, it is constraining xj to be between L2 and U2 and so forth. In the distance graph, what does that mean? It means the addition of a forward edge, from x0 to that variable annotated with the upper bound, and the reverse edge annotated with the negation of the lower bound. So if I make a set of commitments to the disjuncts, and if there happens to be an inconsistency, okay, then it must involve one of these newly thrown in edges, right? That came about by virtue of making my commitments to these disjuncts. But every time I make a commitment to these disjuncts, that involves the addition of these edges. So a forward edge from x0 to that variable annotated with the upper bound, and the reverse edge annotated with the negation of the lower bound. So if there were no inconsistencies before, and if there is an inconsistency now that's newly created by committing to certain disjuncts, it must involve one of these newly thrown in edges. And if it must involve one of these newly thrown in edges, it must involve x0 because x0 is at the end point of every such edge. And if it must involve x0, it can involve at most 2 such edges. What does it mean? It means that if there are conflicts in my system by virtue of the commitments that I make, well, guess what? At most 2 of them contributed to that conflict. There are no higher order conflicts. It had most two of my commitments that created a conflict. Okay, which means if anything at all, our meta-level CSP is only a binary CSP. So in order to establish the notion of smoothness for binary constraints, now I need to tell you what is going to be a good ordering on the domain values of all the variables, right? So what is a good ordering on the domain values of this meta-level variable associated with this disjunct, right? So the disjuncts are the domain values now for these meta-level variables. What is a good ordering on that? Well, in increasing order of those intervals. What is a good ordering on the disjuncts of this constraint? Well, there is no natural ordering, but then there are only two disjuncts, so either way is fine. Okay, so under this ordering of the disjuncts, the meta-level CSP is going to be smooth. All right, but we don't have to stop there. In my AAA paper in 2006, I showed that essentially temporal reasoning problems where the relative execution times of two events are constrained not just by simple temporal constraint, but something arbitrary looking like this, right? They're still going to be strongly polynomial time solvable. As far as in the geometry, they look smooth. The feasible region looks smooth. Okay? Yeah, Thomas?
The Meta-CSP, is there a polynomial time reduction from the original problem?
So the thing is, the meta-level CSP, because we showed that it was only a binary CSP, we could enumerate all the constraints beforehand. And because at most two variables are going to participate in a conflict, right? So at least the process of enumerating the constraints is going to be simple. That we know from this distance graph reasoning, right? No. So for every disjunctive constraint, we create one variable. Its domain values are just the disjuncts in that constraint. Okay. All right. So remember the trick I mentioned that if we have a polynomial time randomized algorithm for solving a certain problem, then we are very likely to find a deterministic polynomial time algorithm for it also, right? And we play the trick here. So let's look for a deterministic algorithm for solving the kinds of disjunctive temporal problems that I showed you were smooth and therefore amenable to a randomized algorithm. Well, it turns out that if you actually go ahead and do this endeavor, then you would be surprised because something comes for free, right? So there is in fact a max flow based algorithm for solving these kinds of disjunctive temporal problems. But when you do this, work through this process, something comes for free, which is that you can also begin to reason about preferences, not just constraints, but added preferences. For example, this one here, we are given a simple temporal constraint as before, but now I'm going to associate a preference, okay, for x2 being scheduled within a certain time frame. And so there's a preference function associated with every variable, right? So this is the preference function. So if x2 is scheduled between 9:15 and 9:30, you have a good preference, but between 9 and 9:15, you have a low preference and so forth, right? Now, if these preference functions are piecewise constant, right, then I claim that the max flow algorithm for solving the disjunctive temporal problems can also solve this, where we can satisfy all the constraints, plus maximize the sum of our preferences associated with each of the variables. I'm going to walk you through some of the max flow based ideas here just because they're so interesting, but I'll do it in the context of a slightly different problem, one that we published last year in AAA High. So here we are given a simple temporal network like this. I mean, you could have events as well as processes in there. A process really would be modeled as two events, right? One for the starting point and one for the ending point, right? And now on the timeline, you're also given certain taboo regions in your time where nothing can be scheduled, right? So no event can be scheduled in that region. Neither should a process overlap with the taboo region. Taboo regions could come about because of certain maintenance periods that you have to respect, or maybe periods of low battery power where you would better be recharging yourself than executing a task, right? And now the question is, can I find a schedule for all these events such that not only all the constraints here are satisfied, but no event gets scheduled within any of the taboo regions here, plus none of the processes overlap with the taboo regions here. Okay? And it turns out that if you actually write down the constraints, they fit the smooth constraints, the kinds of disjunctions that I was speaking about. They fit those kinds of disjunctions, and therefore this is a tractable problem. But if you look at it from the perspective of max flow, you get something for free, which is that you could get even the soft version of the problem for free. So often it can happen that it's impossible to keep all the processes out of all the taboo regions, and maybe the problem is constrained in that way. In such a case, we would like to kind of associate a penalty function for every process taboo region overlap, right? And we want to minimize this penalty, the cumulative penalty. All right? So let's once again look at how we could solve such a problem using a visualization here. So for every process taboo region pair, I create an oval, right? There are two ways of avoiding an overlap between this process and taboo region. Either the process starts after the taboo region finishes, which I'm going to call the NR node, right? So those two ways are going to be represented by these two internal nodes within that oval, right? So either the process should start after the taboo region finishes, which means, it's going to be this node. The B2, which is the endpoint of T2, should be before the starting point of P1, right? Either that should be the case, or the reverse case, where the process should finish before the taboo region starts, right? So the endpoint of P1, XCP1, should be less than or equal to A2. Right, so these are the two possible ways of avoiding an overlap between a process and a taboo region. Right? I just call them NL nodes and NR nodes.
Why do you call this soft version?
Because the hard version of the problem is just to satisfy all the constraints. Right? Avoid all the processes being from any of the taboo regions. That you may not have such a solution. It may be impossible to come up with such a schedule. So in such a case, you would want a softer version of the problem where you associate penalties and minimize the penalty. Right?
So how does the algorithm for respect to the number of taboo regions?
It's all polynomial. This is a polynomial time. It's amazing that it's a polynomial time algorithm. Actually, even the design version of this problem is polynomial time. I'll tell you about it in a second. So these are my NL nodes and NR nodes. And those are the semantics associated with those nodes. Once again, if you look at what happens in the distance graph, whenever I try to resolve an overlap between a process and a taboo region by enforcing one of these constraints, what happens in the distance graph? Well, if I go along with this constraint, right, that means the addition of an edge from x0 to that variable annotated with aj, and the other possibility is the addition of a reverse edge from that variable to x0 annotated with minus bj. Once again, we use the same pigeonhole argument. If there is a newly created negative cost cycle, it must involve one of these newly thrown in edges. And if it must involve one of these newly thrown in edges, it must involve x0. And if it must involve x0, it can involve at most two such edges. And even in the case when it involves at most, in the case that it involves exactly two such edges, one of them has to be incoming to x0, the other one should be outgoing to x0. Outgoing from x0, right? So what does this mean? It means that we will never have a conflict between two NL nodes or between two NR nodes. The conflict will always be between an NL node and an NR node. All right? And there are no higher order conflicts in the system. They're all binary, which means that I can simply enumerate them and represent them as edges here in this graph. And this is going to be bipartite because I just said that because x0 will have to have one incoming edge and one outgoing edge, and incoming edges are contributed by the NL nodes, outgoing edges are contributed by the NR nodes. A conflict will always be between one guy from this side and one guy from this side, but never between two of the same side. Okay? So which means that since all the conflicts are encoded as edges here, a feasible assignment corresponds to an independent set, and our optimal solution corresponds to a maximum weighted independent set here. The maximum weighted independent set problem is unfortunately NP hard to solve in general, but for bipartite graphs, it's polynomial time solvable using max flow. Right? So it's actually pretty amazing that this interesting problem is polynomial time solvable. And in fact, like I mentioned, even the design version of this problem is easy to solve, which in the design version of the problem, you are not given the taboo regions. You are asked to design it by yourself. and maximize the length of the taboo regions, right? What does that mean? It means maximize your idle time. If you're a robot and you have all these various processes to finish, all these various tasks to finish with all simple temporal constraints between them, and if you're asked to design a taboo region, essentially your idle time, maximize your idle time, that's conserving your battery power. It's amazing that this is a tractable problem. Plus, if you're an office workflow environment, it essentially means that, keep your office open as little as possible so that you can minimize overhead costs, right? Like I said, it's pretty cool that this is a easily solvable problem. Plus, most of the intuitions for solving it actually come from the notion of smoothness. Yeah.
So how, what's the complexity of determining if a constraint is smooth?
Oh, that's just local, right? I mean, you look at each constraint individually, and then you just, well, I mean, it's, so if the domain size of a variable is D, and the other one is D2, right? So D cross D matrix, right? I mean, that's not.
Well, you have to compare distance for every point, every unfeasible point to every feasible point.
No. We do not have these. We do not know what the feasible solution is a priori. All we are arguing is that.
How do you determine that a constraint is smooth?
By looking at it locally. By looking at it locally.
And what's the complexity of that?
It's quadratic, but it doesn't matter, even if it was exponential, because it's a local thing. At most, 2 variables are participating there, right? Or let's say at most k of them are participating.
You're a very large constraint.
Right, yeah, okay. But I mean, it's quadratic. It turns out to be quadratic, right? All right. So very quickly, if I have a little bit more time, I do want to move on to the other idea of reasoning about general combinatorial problems using the constraint composite graph, right? Once again, it's a very local approach which gives you these insights into the nature of your combinatorial problem just by essentially eyeballing it, right? So in the weighted CSP framework, which is generalization of the CSP framework, by the way, you have a bunch of variables, x1 through xn. Each variable has a discrete domain. Why isn't this working now? Each variable has, okay, each variable has a discrete value domain di, much like before. But this time, the constraints are going to specify a cost for every possible combination of values to the subset of variables, right? Instead of specifying whether or not it's allowed, it specifies a cost. And the goal is to come up with an optimal solution, which is an assignment of values to all the variables from the respective domains such that the total cost is minimized. Okay? So let's look at, say, the min-ST cut problem that can be modeled as a weighted in the weighted CSP framework using only Boolean variables, right? So in the min-ST cut problem, you have a graph like this, and with 2 nominated nodes, S and T, and you want to kind of put the S on one side, call it the left partition, and T on the other side, the right partition, and you want to cut as few edges as possible in between. I mean, you could weigh the edges if you wanted to, right? So let's call the 2 partitions as values 0 and 1. Right? I'm going to associate a variable with every node. Right? So S has a unary weighted constraint on top of it, which is essentially saying that the cost of assigning it to the left partition is nothing, but the cost of assigning it to the other partition is infinity, which means that it got to reside here. Similarly, T has got to reside there. But for any intermediate node, it could be either 0 or 1, go to the left partition or to the right partition. And there's a cost associated with whether the endpoints of an edge are going to be cut or not, right? For example, there's an adjacency relationship here between x3 and x4, and the weight on that edge is 5. Well, what does that mean in terms of the weighted constraint? If x3 and x4 are assigned to the same partition, namely the 0 partition here, then they get a cost of 0 because it's not really cut, right? So on the other hand, if x3 and x4 are assigned the value 1, they both belong to this partition, they're not cut, once again 0 cost. But if one of them gets assigned to that partition and the other one to here, then we bear a cost and we penalize it by an amount equal to the weight of the edge, right? So we can model the min-ST cut problem using the weighted CSP framework. Similarly, we can model the max cut problem also using the weighted CSP framework. So here we are asked to maximize the number of edges that are running between the 2 partitions without having 2 nominated nodes S and T. And here the binary constraints are going to look flipped around. So we actually prefer them to be in different partitions like this one, and we penalize if they're in the same partition. Okay. So what is interesting to note here is that both the max cut problem and the min cut problem could be modeled using the weighted CSP framework, using only Boolean variables and only binary constraints. All right. But yet one of them was NP hard, max cut is NP hard, min cut is polynomial time solvable. Right. So even when we restrict ourselves to Boolean variables and binary constraints, still the kinds of problems that we can talk about differ a lot in their complexity classes. On the other hand, in constraint satisfaction problems, if you restrict your variables to be Boolean and your constraints to be binary, that's just two set, that's just polynomial time. Right? But here, you still have a differentiation in complexity classes. So this explains why people have had such a hard time wrapping their heads around, reasoning about this general framework of weighted CSPs. By the way, probabilistic reasoning problems are also going to fit into the weighted CSP framework just by taking the negative logarithm of the probabilities, right? Essentially the same thing as weighted CSPs. So what I'm going to show you now, so traditionally there have been two approaches to solving weighted CSPs. One is, you analyze the structure of the constraints themselves. Maybe you've identified them as belonging to some tractable class of, some known tractable class of constraints, the so-called numerical structure of the constraints. Or if you're not able to do that, you simply say, okay, let's look at the graphical structure of the constraint network. Let's just look at which variables are constrained with which other variables. And maybe if they look like a tree, then we can say that they're polynomial time solvable, or we can characterize the tree width of this constraint network and so forth. So that's exploiting the graphical structure, right? So these are two disparate ways of analyzing combinatorial problems. But I'm going to show you this unifying framework that not only unifies the graphical structure and the numerical structure, but also is a very local approach, right? So let me. The idea is to begin with this graph theoretic notion of the projections of minimum vertex covers onto independent sets. All right. So this is a concept that I'm going to speak about. So you have to bear this problem that we originally had about reasoning about weighted CSPs. But here I'm just giving you a graph theoretic concept of projecting the minimum vertex cover onto an independent set. Right. So let's say that we are given a graph like this with nodes having weights associated with them, plus we are also given an independent set, let's say x1 and x4, right? And we can define, and the output is going to be a table that's exponential, not a single number, but a table that's exponential in the size of the independent set, this one here. So for every combination of Boolean values to these variables, right, I have an entry, right? That's going to be my output. What do these entries correspond to? First of all, we use the semantics that 0 means that variable is going to be absent from the vertex cover, and 1 means it's going to be necessarily present in the vertex cover. Okay? So why is there a 5 here? The reason there's a 5 there is because what is it saying? x1 equal to 1 means that x1 has to be necessarily chosen in the vertex cover, so that's a commitment that I already made, so I keep it apart, so that accounts for 1 already. The other x4 equal to 0 means that x4 cannot be chosen in the vertex cover, so I give him a weight of infinity so that he will never be chosen. And in the remaining graph, the size of the minimum vertex cover is the choice of these guys. Right? So that accounts for a total of 4. So put together, that's 5. That's the reason why 5 is there. So if you look at this concept of projecting the minimum vertex cover problem onto an independent set, it gives you a table, right, on the participating variables from that independent set. This table looks suspiciously like a weighted constraint between those variables. So now you can ask the reverse question. Can I take any weighted constraint and give it a lifted representation in some graph with all these auxiliary variables such that it can be looked at as the projection of a minimum vertex cover problem in higher dimensions? Okay, that's the first question. The second question is, what is the benefit of doing this? Well, both have positive answers. It's actually very easy to construct a graph that gives a lifted representation for your weighted constraint. And the second, but let me answer the second question first, which is, what is the benefit of doing this lifted representation thing? So please give me 5 more minutes, if that's fine, right? So what is the benefit of giving lifted representations for constraints, right? So let's look at an example here, right? So here are 3 variables. Here are 3 variables, right? and these are my constraints that someone gave to me, right? So there was a unary constraint on x1, so x1 equal to 0 has a cost of 0.8 associated with it, x1 equal to 1 has a cost of 0.2 associated with it, and so forth. So 3 unary constraints and 3 binary constraints, like this one, right? It turns out that the optimal solution here is 1, 0, 0. So x1 equal to 1, x2 equal to 0, and x3 equal to 0 is the optimal solution. That minimizes the cumulative cost, right? But in order to solve such a problem, I'm going to do graph-based reasoning. Why? I'm going to look at each constraint individually, right? So I looked at that constraint just by itself, without regard to the other constraints. I can give it a simple lifted representation, right? x1 connected to a4, right? Some auxiliary variable a4 through a single edge. Why is this the lifted representation of this guy? Because when x1 equal to 0, what does it mean? It means that he's not going to be in the vertex cover, so I have to choose this guy to cover this edge. So that accounts for 0.8, right? So when x1 equal to 1, that means he's going to be in the vertex cover, so he's going to cover that edge already, so I don't have to pick the auxiliary variable, right? So this simple edge is a lifted representation of that constraint. How about these binary constraints here? Why is this simple V structure a lifted representation for this guy? So let's look at it. So x1 equal to 1 and x2 equal to 0. Let's look at that case. When x1 equal to 1, he has to be in the vertex cover. So 0.2 comes from there. And x2 equal to 0, he cannot be in the vertex cover. So I have to pick this guy in order to cover this edge. So that's 0.5. So that explains the 0.7 there. So every constraint, I look at it individually, give it a lifted graphical representation. So what do I have now is a bunch of these little graphs where all the auxiliary variables are named uniquely. There's no repetitions, right? The only repetitions are the original variables. x1 here comes with a weight of 0.2, x1 here comes with a weight of 0.3, and there with a weight of 0.2, right? Now I'm going to build this composite graph, which is the simplest way in which you can conglomerate all these individual graphs. Right? So I simply look at each of these nodes, A4 with weight 0.8, right? So I just put A4 with weight 0.8, A1 with weight 0.5, and so forth. So A1 was connected to x1 and x2 because that's how A1 was here. A1 was connected to x1 and x2. So I simply connect him up in this composite graph as well, right? Okay, the weights on x1, x2, and x3, however, are the total weights. So for example, why does x1 have a weight of 0.7? That's because it's the cumulative weight here. x1 equal to 0.2 plus x plus 0.3 plus 0.2 there, right? So I have this composite graph that essentially is built out of the individual little lifted representations for each constraint. And the claim is that if I solve my vertex cover problem on this graph, that encodes a solution to my original problem, right? So if I solve the minimum vertex cover problem here, those are going to be in my minimum vertex cover, right? That encodes a solution for the original problem, because I simply go and ask the question, was x1 chosen to be in the minimum vertex cover? If yes, he is going to be set to 1. Was x2 chosen to be in the minimum vertex cover? No, his optimal value is 0, right? Was x3 going to be chosen in the vertex cover? No, so his optimal value is 0. So that encodes a solution to the original problem. All right. So what is this telling you? It's telling you that essentially you can look at each of these graphs individually, each of these constraints individually, build lifted representations for them. The composite graph that represents a lifted representation, which gives you a lifted representation for the entire problem, is a simple conglomeration of these things. So if each of these individual graphs is bipartite, for example, the composite graph is also going to be bipartite. Right? And we know that bipartite graphs, minimum vertex cover, can be solved in polynomial time. So the language of all weighted constraints that have lifted bipartite representations is a tractable language. So the first major result in the general study of weighted CSPs that I published in 2008. Okay. Okay. I guess I'm running out of time. Okay. All right. Let me stop here, and let me kind of at least put up these. Okay, the important results. So any combinatorial problem has a tripartite composite graph associated with it, and the tractable class of problems that people had identified bearing different intuitions in mind, like submodular constraints and and the min-cut constraints or hypergraph min-cut constraints. They're basically the numerical structure of the problem. Basically, they correspond to bipartite CCGs. But the tree width of a CCG is still going to be the same as the tree width of the original constraint network. So it has both the graphical structure as well as the numerical structure encoded in there, right? So it's kind of a unifying framework. Okay, let me stop here. There are other things that I want to talk about, but we can talk about it in individual meetings.
Yeah, so we really went quite a bit over. So maybe you can save your questions for, we have a lot of meetings and we get to all that. So let's thank our speaker one more time.